Hi, I'm Tom Dick. I'm a math advisor for Texas Instruments, and this video is part of the TI-Nspire AP Calculus series. We're going to use free response question 2 from the 2019 BC exam to take a look at polar curves. Let's get started. This was the curve that was presented on BC question 2 from 2019. It shows one leaf or petal, if you will, of a polar curve. The domain of this curve was from theta ranging from 0 to square root of pi. Let's take a look at the formula for the curve. So I'm going to go to the other half of this window where we have a notes page. I'm going to insert a math box, and I'm just going to recall the formula for R1 of theta, which is what's plotted here. So I'm just typing in R1 of theta, and I'm pulling up this little special menu to get that symbol theta. And there we go. This was the formula, and this was also presented on the exam question. Okay, so one part of this question asked to find just the area enclosed by that curve. So I'm going to, in another math box, do a calculus calculation. So I've called up the integral, and we just want to integrate from 0 to square root of pi. That's the domain for this leaf. So I'm entering those as my bounds of integration. And now for our integrand, to find the area enclosed by a polar curve, we integrate 1/2 times the square of our polar function. So you can see that I've entered 1/2, and now I'm going to enter that R1 of theta again, but I need to square that. And so let's get that entered. And we want to make sure that we don't forget to square that R1 of theta value. So let's get that square in there. And then, of course, we need our variable of integration, theta. So I'll pull up the theta symbol one more time. And that should do the trick. So let's enter that. And we see that we actually get a symbolic, well, it is a numerical answer, but it's using the symbol pi. 9 pi over 8. Now, if we did want a decimal version, if we just edit our integral to include some decimal value somewhere, and the most convenient one here for, I thought, was to just add a decimal point to the 0 on that lower limit of integration. And here's the decimal value that's equivalent to 9 pi over 8. All right. Now, let's take a look at part B of this problem. And this asked for the average distance a point on the curve is from the origin over that entire domain from 0 to square root of pi. Now this is an average value. The length of our interval is going to be square root of pi to 0. So I entered 1 over square root of pi. This is to get the average value over the interval. And then we'll integrate from 0 to square root of pi. So I'm entering those bounds of integration from 0 to square root of pi. And the distance from the origin is actually just given simply by our function R1 of theta. So that will be our integrand, just the function R1 of theta. So I'll enter that as my integrand. And finally, we need to put in the variable of integration theta. So I'll pull up the symbol theta one more time. And taking that integral, dividing by the square root of pi, which is the length of the interval, gives us our answer of 1.57993. So let's move to a new page now. This is another split window, but you can see it's split in a different way. I've got my polar curve graphed again, but we also have a line that goes through the origin, which has an equation of just y equals mx, and I have a slider that's controlling the value of the slope m. So this little slider, as I increment the value of m, you can see that's changing the slope of that red line. All right. Now let's illustrate a key idea in this question, and that is relating the angle the line makes to the positive x-axis to the value of the slope m. So I've gone to the geometry menu, and I'm putting 3 points that are determining an angle and measuring it. So this is measuring that angle that I want, that the line makes with the positive x-axis. I'm going to actually change the precision that's displayed here so we see a few more decimal places. So now I have this live angle measurement. I call it live because it will be updated as I change the slope. So as I change the slope of the line, we can see that the angle is changing. Now, is there another way to determine that angle? Well, I've gone down here to the other half of the window and I've inserted a math box. I want to just illustrate another way we could calculate that angle is using the inverse tangent of the slope. Notice that's exactly the same value, at least to 6 decimal places, that's reported as that angle. As I change the value of the slope, you can see both of those values are changing and they're always equal. Why does this make sense? Well, the slope of my line, if I imagine a little triangle in there, that would be the slope would be given by the opposite over adjacent, or the tangent of that angle. So by taking the inverse tangent, we recover the angle back. So that's a nice way to calculate that angle directly from the slope. Part C asked what value of m would divide that leaf into 2 regions of equal area. Well, now that we know the angle associated with that dividing line, we could set up 2 integrals representing the 2 areas. And on this next page here, I've gone ahead and entered those 2 integrals. What I'm calling g of m is the area from the start of the interval, 0, up to the angle determined by the line. H of m represents the area from the line to the end of the interval, square root of pi. Now we could actually see how good a job we did with our slope of 3.1. So I'm going to ask for the value of g. This would be the area up to the line. That's 1.79789. And now let's ask for the value of h of m. That would be the area from the line to the end of the interval. And our value of h of m is 1.7364. Not bad, but not exactly correct, or not exactly equal. If we wanted to solve an equation to find the exact value, I could just go to a math box, go to the algebra menu, pull up solve, and I've gone ahead and labeled these 2 integrals, g of m, h of m. I'll go ahead and use the shorthand here. So we'll solve g of m equal to h of m for the value of m. Now in the actual AP question, it just asks you to set up the equation that would give you that value of m. Here we're going to go ahead and actually solve for it using the solver on the TI-Nspire. And there we go. We actually get 2 values, one of which we're not interested in, the negative one. But here, that positive value, 3.04, we can see that we were indeed close with our eyeball estimate. All right, let's wind up with part D of the question. I've gone to a fresh page where we just have our polar curve again. I want to graph another curve, another polar curve, so I've called up the polar graphs. We've already got R1 of theta. Our R2 of theta, we're going to put in a formula that will give us a circle. And we're going to parameterize it by this constant k. So our formula is just going to be R2 of theta equals k times the cosine of theta, where k is a constant. Now I've not declared k anywhere else. By the way, this interval, notice the default interval here is from 0 to 2 pi, and there's the default theta step. We'll just go ahead and stick with those. Now when I enter this, it asks me if I want to create a slider for k. We'll say OK. And let me move the slider down here. And it kind of comes up with these default values. I'm going to go ahead and change the settings for that slider. And let's see what we should change them to. I'll tell you what, we'll stick with an initial value of k, but we'll let k range from 0 to, say, 100. And let's go in steps of just 1. So I'll set the step size to 1. And just, we don't need like a tuner bar slider. I'm just going to minimize it. Gives us this little pointy arrow slider. And I can now see with that value of k equal to 1, we get a circle of actually radius 1/2. If I change the value of k to 2, I get a circle of radius 1, centered at 1. Every circle goes through the origin, and its center is always on the positive x-axis. So we can see we get a succession of circles here. And question part D asks for the limiting area of this overlapping region inside both the circle and the leaf as k approaches infinity. Now I'm continuing to increase the value of k. Let's go up to k equal 24. We've got a very large circle now. I'm actually going to jump all the way to the top value of my slider, which was 100. And we can see that the circle, as k increases, that part of the circle begins to resemble the y-axis. That gives us a clue to our limiting value will be represented by integrating from 0 to pi over 2, which is the angle the positive y-axis makes with the positive x-axis. Now I've just gone back to our original first page where we calculated the original area of the leaf from 0 to square root of pi. I'm replacing that square root of pi with pi over 2, which will be the limiting region. And now we can see the area that we're after is at 3.32447. Well, that winds up this short video. For more resources like these, please see education.ti.com.